All right. So, hello, namaste, and welcome everyone. Uh, I cannot see any participant today here in this meeting, so maybe I will just record this lecture and upload it. And if you feel, you can always ask question in other sessions. Okay. So let me just share my screen. Okay. So I am doing all this from my understanding. From what I can see on my screen, I am. So I'm not able to basically verify if everything is visible to you, but hopefully in the recording it is visible. Okay. So, um, so this is tutorial 8, right? Okay. All right. So welcome everyone. So today we will be basically going through stuff from week 8 of of this course, right? So before this week, in week 7, we basically saw something called bias variance trade-off, and we saw how regularizations can actually help us, how regularizations can help us. Okay, so hello, namaste, and welcome. Uh, right, so today we will be basically covering stuffs from week 8, right? So basically, in week 7, what we saw was something called bias variance trade-off, right? Uh, After bias variance trade-off basically showed us some important concepts of deep learning. In particular, we saw that how bias is defined, how variance is defined, and how these terms help us in defining underfitting, overfitting, and things like that. How to avoid memorizations and stuff. And then we saw that with this framework of bias variance trade-off, how you know uh, regularization comes in and how it helps us in actually uh, uh, tackling this issue of say underfitting or overfitting. In particular, we saw something called bias variance trade-off curve, and then from there we motivated that how uh, actually using regularization can actually help you hit the sweet spot. Uh, these are the stuff that we discussed it last time. So, so since week 4, we have been basically what we are doing is we are going into nitty gritty details of deep learning. Okay, in more specifically, we are saying okay, what are the possible problems that we will face when we actually do deep learning. So, earlier we saw, so I think week 4, week 5, we saw something called curse of dimensionality, which is one of the practical problems that we face in deep learning. Then in week 6, we saw underfitting, overfitting, and then we saw how regularization helps us with that. So week 8 basically goes into even more finer details. Well, not mathematically, but practically speaking. Why so basically when people started doing deep learning, they observed that so as you might be aware that deep learning is something that has recently boomed a lot. I mean, it was not as famous as it is today. Let's say some 10-15 years ago. Okay, So most the major reasons behind this thing is, one of them is, today we have access to, very large compute powers. We cannot deny that, that is definitely one of the things that has helped us a lot. And the other thing is, we have much better understanding of, why something works, why something doesn't work, and things like that. So, in week 8 material, what we are going to see is basically something called, what is the effect of, different activation functions. What are the pitfalls of different activation functions, and also, you know, so also we will be basically saying, so, even so going even into finer details tells us that, even initialize how you initialize your network is a important thing, and, it that which determines a lot, how your network is going to be trained and stuff like that. All right. So, tutorial 8, so week 8 was very concise. Let me write it down. Uh, week 8, uh, effect of different activations, okay, and effect of different initialization, okay. uh, right, so these are basically broadly the two topics that is covered in week 8. And speaking of which, actually, I personally feel that, in other courses that are available online, these aspects are generally not covered. So it is really something that is, worth praising. That, for example, let's say four or five, like, so let's say when I started my PhD, I didn't know, how does initialization even why should even initialization even affect your training process and neural nets. But, when I saw that, okay, there are actually mathematical proofs that tell you that, okay, it does affect your training process and your network. So it kind of opened my eyes. So basically what I learned from these topics is that, nothing comes from out of the box. I mean, it's not like, someday someone tried something and something and it worked and now we are using it. So there is proper explanation for everything. And so nothing is free. There is, in some sense, everything is well studied, and more or less we have proofs and, guarantees for all the things that we do in practice. Okay. Having said that, um, so let's see what these things are. So actually these things, so week eight's topic are not that broad. It's mostly, discussing things. So what I intend to do is, I will, maybe I will start with, maybe motivating these topics. Why is it essential to look at these stuff? Effect of activations and initializations. However, I won't cover each of these topics as it is already covered in the uh, uh, video lectures. However, I saw the questions, and, I feel that as we solve the questions, anyway, we will be covering all those topics, so it should not make any difference. Okay. Okay. So let me maybe motivate these things. Okay. So first of all, we need to remember what are activation functions. Okay. So maybe, some few weeks back, what we saw was, feed forward networks. So if we remember, some we studied something called feed forward networks. Okay. What are feed forward networks? Basically, you have a set of inputs. So let's say let's say it's n dimensional. So you have, let's say, x1, x2 till some xn. Okay. So these are your inputs. You basically apply a linear combination and a non-linear transformation at each layer, and pass your transform your input in successively. So what I am basically saying is that, let's say, this is your next layer. Okay. It could have any number of neurons, doesn't matter. Okay. So maybe connected like this, right? So maybe this is how these things are connected, right? uh so 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 let's say if this was Rn, and this is, let's say, Rm. Okay. uh, what how do we calculate the outputs of this layer? Basically what we do is, so let's call the this entire input as some capital X. Okay. So we take a weight matrix W and multiply it with X. All right. Add some bias term, right? And we pass it through a non-linear function. Let's we denote it by sigma. Okay. And the sigma is what is called as your activation function, right? This is your activation function. What so X, let's say, is so let's say each of uh, so let's say your batch size is some B. Okay. So okay, so we have already used B. So let's say capital B. So let's say X has a dimension of n cross capital B. Okay. Then what should be the dimension of your weight matrix? It should be, so it has to give something in Rm, and it has to take something from something in Rn. Okay. So to match the dimensions, so that the matrix multiplication is correct, it should have a dimension of m cross n. And what would be the dimension of B? The dimension of B would be the same as the dimension of the outputs of this layer, uh, uh, which is what, Rm, right? So this should belong to Rm, right? So this is basically one layer. You have multiple successive layers. Okay. So there are a lot of layers, uh, and finally, let's say maybe you have only two classes, so you have two outputs, and you output something, from this using a similar concept. So basically, it's successive application of a linear transform followed by a non-linear transformation, which we call activation functions. And this entire thing constitutes one feed forward network, right? So this is something that we have already seen. Okay. Uh, well, now, one a natural question to ask here is, so how okay, so then how do we learn things here? The thumb rule is that of gradient descent. Uh, by now we should be very familiar with this thing, gradient descent for learning. So there are multiple uh, algorithms. There is adaptive movement, RMS prop, and other optimization algorithms, but all of them branch out from gradient descent. So whatever I say for gradient descent follows for other optimization algorithms as well. Okay. So how does it? What is the rule for gradient descent? So let's say you have some parameter theta. Okay. At iteration, let's say I plus one, right? This parameter is updated in the following way. It is theta I minus some alpha, which is your learning rate, times gradient with respect to theta L of theta, comma, let's say y hat. Okay, whatever it is, evaluated at theta I. This is how this is basically your gradient descent algorithm, right? So, and what is your what is this L here? L here is your loss function, right? So the idea is you take your input, pass it through the network. The network will predict something and see if this prediction is close to your actual output using some loss function, which is your L here, right? And then use this L and gradient of L with respect to this these parameters theta to obtain this term and update your parameters in this fashion, right? So basically, you can imagine that there is some loss curve which looks something like this, okay? And I'm just drawing something. It can be even weird, okay? Well, you have started from some point, let's say, which is here, and you want to minimize this loss function. So what you are doing is essentially you are going in the steepest descent direction. So maybe here, and so maybe you will essentially reach the minimum. Okay. Okay. So this is the whole idea. You want to reduce your loss function. I mean, reducing your loss function is equivalent to saying that you want your predictions to be as close to the actual outputs as possible. Okay. So this is the basic general idea of neural networks, in particular feed forward neural networks. Okay. Well, there are some things that we need to worry about, right? So for examples, I mean, some of these we have already seen, right? So there are a lot of hyperparameters. Okay, let me write this down. Uh, there are a lot of hyperparameters. So what are hyperparameters? Well, theta here is your parameter, right? Which is the parameter of your network. Okay. Well, hyperparameter are those quantities which basically decide the value of your parameters. Okay. So you can imagine by word, I mean, you can guess by the naming itself that hyperparameters are something that you use to learn the parameters itself. Okay. So, so what are the hyperparameters in your let's say this given feed forward network? Well, maybe I will list some of them down. Okay. Uh, so so one possible thing is how should this architecture even look like? I mean, how many layers should be there? How many neurons should be there, and things like that. So one can say that architecture itself is a hyperparameter architecture. How many neurons, what should be the depth of your network and stuff like that, right? Well, uh, another hyperparameter could be your step size alpha, step size alpha, which is here, this thing, you know uh, I mean, we don't know, when there is no thumb rule to choose an alpha, but when we were doing these assignments on optimization, we saw that uh, what is the effect of choosing different values of alpha? What if we choose a large alpha? What if we choose a very small alpha? And stuff like that, right? So this is something that we have already studied, right? So maybe already studied. Let me just write it down. Already studied. Another hyperparameter could be, say, let's say, what should be your activation function itself? You know, activation function. I mean, we don't know what this thing is, right? I mean, how do I know that if this is a correct activation function, or should I change it or maybe see something else? That is another. And another hyperparameter, you know, so one of another hyperparameter, for example, could be batch size, let's say, right? So which is B. So here we are using a batch size of B, right? So what should be my batch size? That also, I mean, that is also something that is, that is up to us. I can choose anything I want. So, I have to be careful. I mean, should I choose a large batch size? Should I choose a, small batch size and stuff like that, right? Further, what else can we think of? Let's see. Number of epochs. How many? So, number of epochs. So, I know that I have to run this gradient descent, okay? But for how many times, so should I run it for, let's say, 100 times, or should I run it for 1,000 times? So I don't know, right? I mean, so what is written in textbook is, we should run it for large enough, right? But, large enough is a very vague term, vague word, right? So, I mean, it's a very vague phrase. Should I run it for 2,000 times, or should I run it for, let's say, just 500 times? I don't know. That is another hyperparameter, right? And another thing could be, how do you initialize your network at all? So this is a iterative algorithm. I hope you will agree with me. So there has to be some theta naught to start with, right? I mean, it is, I mean, so there is no, I mean, there is no way to, just, it won't happen that, theta, this algorithm will get initialized automatically. We need to initialize it from somewhere. So that is another hyperparameter, right? Initialization. This is theta, right? So I mean, as you go move forward in this lectures, maybe when you see convolutional neural networks and some architectures in NLP. So this is just for a simple feed forward network, okay? When you go in even some complex stuff like, uh, especially something like convolutional neural network, there is something called filter size that will come in, which, again, is a hyperparameter. You don't know. So what I want to basically say is that there are a lot of hyperparameters, and depending upon your application, depending upon, you know uh, uh, what your goal is, what your aim is, these things can, change. These are broadly so these are something that are broadly present in almost all the architects, all the problems. But it is not that, only these hyperparameters are there and there cannot be other hyperparameters. In fact, there can be billions of hyperparameters actually, okay? So having said that, uh, uh, in week 8, in today's problem solving session, what we are going to see is basically the effect of uh, two of these things. One is this activation, okay? How does different activation affect the net learning of the network and things like that? And other thing is, this initialization. How does initialization affect your training process, right? So week 8 was mostly focused on these two topics, and it's a small, I mean, relatively, you might have felt that, it is a small, uh, a module. It's not a big module, right? And relatively easy as well, right? It's not very tough or something like that, right? All right. So as I said, the plan is to, solve the questions, and simultaneously I will also explain the concepts that are involved in the problems that we are asked to solve, right? So I hope that should work, because there honestly there is not much to actually explain in this week's content. Last time, there was a lot of content, and it was important as well. This is also important, but I think we can manage it by solving the questions and, explaining it simultaneously. So let's move it that way. If you have any issues, or if you have any questions, you can just unmute yourself and ask, or maybe write in comment and things like that. Okay. So so let's start with some problems, and I mean, I will explain the concept that is used simultaneously, right? Okay, so here is the first question. The first question basically asks you that we have to choose the incorrect statement, okay, with respect to unsupervised pre-training, right? Unsupervised pre-training, okay. So here is so what is unsupervised pre-training at all, right? That is the first question that we should ask. So let me make a loss function, a landscape of a loss function, and I will maybe that should motivate why should pre-training or initialization help us at all. Okay, so consider the following. Okay, so let's say this is your x-axis. I am drawing things in 1D, but it is applicable to higher dimensions as well, right? So let me consider something very simple, right? So let's say this is your loss function, right? So this is your loss function. Okay. Now let's say that you started from, let's say, somewhere here. Okay, and you used gradient descent. Okay, so gradient descent will basically go in the direction of steepest descent, right? So what is the direction of steepest descent here? This direction, right? So we will go here, move down, maybe come here, again move down, come here, and I hope you will agree that we will we will at some point we will definitely come here at this point. Okay, fine. So what is bad with this point? So what is wrong with this point? Well, I hope you will agree that once we have reached here, we won't be able to move away from here, right? We won't be able to move here or somewhere, any other part of this lost landscape, right? Why is that? Well, because you look at the gradient descent loss function. So as soon as this term becomes zero, right? If this term becomes zero, this entire thing becomes zero, right? So you need to ignore this thing. So theta I plus 1 will be equal to theta I, right? So, right, I mean, as soon as your gradients become zero, this entire thing is of no use, and hence from from the point from the moment your gradient has become zero, after that all the iterates will be same, right? Theta I plus 1 will be equal to theta I. That means that you are not moving anywhere further. That's all, right? So is the gradient zero here? Well, yes, if I draw a tangent here, this is the tangent, and it makes 0 degree angle with the x-axis. Hence, it has a it has a zero gradient, right? In general, any optima, minima, or maxima has zero gradients, right? So I have reached here, and hence I won't move any further. Well, this is bad for me, right? Why is this bad for me? Though I have achieved a local minima, okay, this is a minima, right? I hope you will agree with that. This is definitely a minima, but this is not a global minima, right? What is the global minima? Global minima is the so let's say there is a function. There can be multiple minima. So in for example, in this diagram, this is one minima. This is another minima. This is another minima, right? A global minima is the one which is smallest amongst all the minima, right? So in this picture, this one is the global minima, right? In other words, global minima is desired because it tells you that you have reduced the loss functions as much as you can. Okay, here we haven't reduced the loss function as much as we can. Why? Because there is a lot of scope. We can see that maybe if we had initialized our function from here, okay, maybe if we had initialized our function, our parameters from here, we would have moved in this direction, this direction, this direction, and hopefully we would have reached this point. Well, we can see that this minima has a lower loss function, has lower loss as compared to this point, right? Or even if we had initialized our parameters from, let's say, this point, we would have moved here, and hopefully we would have reached this point. This is an even better minimum because value of a loss function here is even less, right? So you I hope you can see that where you initialize your parameters from gives you different answers, different parameters, right? And ha- because of this, initialization becomes a very important uh, concept. You know, let's say, I mean, I hope you can see that, initializing your parameters from this point is bad, or you can say that, this is a bad initialization. Okay, is this a good initialization? Well, this is a better initialization, I think. I mean, compared to this point, this point, this is a better initialization, but nonetheless, this is not the best initialization. However, this point is the best initialization because it gives you the value of the loss function here is the least you can obtain, right? So I hope you can now. I hope this motivates the fact that initialization is something which is very important and you need to keep in mind. Okay. Having said this, what does unsupervised pre-training mean? Okay. So let's say that you had a neural network, again a feed forward network first, let's say. So maybe I will make a simple network here. Let's say it has four inputs, uh, three neurons in the first hidden layer, and let's say it has two output neurons. Okay, a simple network. I'm not making anything which is fancy. Okay, something like this. So what are the parameters here? I hope you will agree that there are there are multiple weights here. So let's say this is how the network is constructed. Every neuron is connected to every other neuron in the next layer. Maybe this one is W11, this is W2, 12, this is W13, and similarly you can name all of them. Well, how do I? So now the question is, how do I initialize all these weight matrices? I mean, these are not the only weight matrix. So I mean, there can be an entire matrix which has the dimension of 4 cross 3. Okay. So how do I initialize this weight matrix to ensure that whatever the loss function that I get, maybe it is a cross entropy loss or something like that here. How do I ensure that initialization from, let's say, this, what should be the initialization so that when I run my gradient descent algorithm, I reach to something like a global minimum. Okay, that is the main question. So one heuristic way. What are heuristic way? Heuristic ways are those which are abstract. There is not a mathematical uh, there is no mathematical what do you call guarantee to it, but nonetheless it works. One heuristic way to initialize this weight matrix is to do the following. So the concept is that you take whatever weights that you want to learn. Okay, so let's say you want to learn these weights, right? So you take the input layer, start from the input layer and go till that layer, which whose weights you want to learn. Okay, so let's say this is the you had four inputs, you had three intermediate neurons, right? And make it a you have a network. Now flip this network so that it becomes a autoencoder. Okay, so if I flip this, I hope you will agree that I will again get four neurons here and three neurons in middle, right? I am so basically make this. I have made this an autoencoder, right? What do I mean? Let's say this was x1, x2, x3, x4, right? And now I am saying that this is x1 hat, x1 hat, x2 hat, x3 hat, x4 hat. Okay. So the idea is that, now basically flipping this network gave it a structure of an autoencoder. Now, uh, unsupervised pre-training, what it tells you is that, train this autoencoder. Okay. So again, I hope you will agree that there's those matrices, the weight matrices that we discussed are still present here. Okay, okay. So I mean, these matrices are still present here. Okay, what we are saying is that just initialize it randomly, do whatever you want, just initialize it. Okay, there will be matrices, some weight matrix here as well. I hope you can see them, right? The idea is to train this autoencoder now. So since this is a so I hope you will agree that this has a structure of an autoencoder. Train this autoencoder, okay? So what does training an autoencoder mean? It means that minimize this loss. Okay, so let's say this is x, this is x hat. Minimize x minus x hat L2 norm of this and square of it. Okay, so take this as your loss function, and let's say you learn w. This is w dash. Learn w and w dash. Okay, using gradient descent or whatever optimization algorithm that you want to learn. Okay, so after let's say you have learned, so after training this autoencoder, let's say you ran it for let's say w 1,000 times. Okay, so the thousandth iterate of this w vector is w 1,000. Now this is your now the unsupervised pre-training tells you that okay, use this to initialize your network. Okay, use this to initialize your network. This is what it tells you, right? So I hope the concept is clear. Whatever layer you are given, whatever weights you want to initialize, take that part of the network, flip it so that it becomes a it it has a shape of it has an architecture which is similar to that of an autoencoder. Now train this autoencoder, right? And whatever weights you obtain after training this autoencoder, use it to initialize your original classifier network or whatever it was. Okay, this is the idea. So why should it work? Well, the a hand wavy explanation is that if when you train this autoencoder, when you train this autoencoder, it has to I mean, as we saw in the previous week, this has to learn something meaningful. Otherwise, it cannot reconstruct the input as it is. Okay, so to reduce this loss, this thing has to learn something which is meaningful. And to learn something meaningful, this w's have to be meaningful, right? Otherwise there is no point in doing all this. If these w's are not meaningful, there is no point. For example, in autoencoder, the week when we saw autoencoders, we saw something. I mean, we saw that PCA is a special case of autoencoder, right? So I mean, we saw all those things that W becomes essentially your a matrix of eigenvectors and things like that. So it was something meaningful. That is what we mean. So if it is meaningful, then definitely it should help us to so it should help us to make this classification problem easier in some sense. Okay, there is some question that is being asked. Uh, there are two queries: exam pattern for deep learning, MCQ, MSQ. What type of question? How many time the files are related to problem solving sessions so far here. Find the others in the website recording and lecture slides. Well, for the first question, I don't know exactly. There, maybe there is an interaction with course instructor. I hope you have received the mail for it. You can maybe ask these questions there. I don't know exactly. Okay. And for the second part, the file slide for the problem solving session, I think there is a Excel file that is shared with you. I don't remember exactly where it is, but in that Excel file, we regularly upload YouTube link to our YouTube channels where we upload these lectures, and we also uh, upload all these materials that are there. Okay, so I hope that answers your second part. For the first part, I don't know. Maybe you can ask it on the forum itself. So someone had raised their hand. Mona, is there any question? I saw you had raised your hand.
Yes. If I am not wrong, to answer question number one, I think the exam marking is similar to the that of assignments. There is no negative marking, and for multiple choice, you have only one choice is correct. But for there are some in which multiple selections are allowed. Usme, I think if any selection is selected which is not part of the multiple selection, then you get a zero. I think it works something like that.
Okay, so basically you are saying that it is very similar to that of us how assignments are
Yes,
graded.
because I have
Okay.
done one other NPTEL course earlier. It worked in that way. So I'm assuming it would be the same in this.
Okay, I see. Yeah, so perhaps that might be the case. Either yeah, I also think that most likely it is going to have the same pattern. However, if you still, just to be on the safe side, you can ask this on the forum itself, the doubt forum. Okay. All right. So yeah, having said that, let's continue where we stopped. So basically, what I was saying was, the weights that you learn by training your this superficial autoencoder, that might be useful. That might be a good choice to initialize your network itself, and that way, maybe maybe you are close to the optimal global minima. Okay. And hence gradient descent would give you a better solution. So this is the basic idea. There is no mathematical justification. you know there is so I cannot so there is no mathematical answer to as to why this should work or why this won't work. It is observed empirically that this does work. Okay. So that is why it is a heuristic method. Okay. So let's come back to our question. The question has the question gives us four options. The first option is, so we have to choose the incorrect statement. So let us identify the true statements, correct statements first. The first one is autoencoders can be used to learn representations from input. Uh, can be used to learn representations. Well, this is correct. Autoencoders are designed to work like that. So this is a correct statement. What is the B option? B option is we converge faster to a minima using unsupervised programming. The convergence is faster. Well, this is also correct. Why is this correct? Because the whole idea is that if this is the global minima, unsupervised pre-training should give you something which is already close to your minima. Otherwise, if it is far from your minima, you can maybe either you will get stuck in a local minima, or you will be very far away from the optima, right? So this is, let's say, if you started randomly, this is what your distance from your optimal minima is. However, if you started from pre-training, this is what your distance from optimal minima is, right? So this is also a correct statement, right? So B is also fine. What is the C option? C option is hidden layers used in feed-forward networks are initialized with random weights. Well, this is not correct, right? Hidden layers uh, in feed-forward network are initialized randomly. Initialized randomly. Well, this is not correct, right? As we see, it is initialized using the pre-trained weights, right? So this is the incorrect statement. So we are asked to point out the incorrect statement. So C is the incorrect statement. So C will be the answer, right? Okay. So this was the first question. Second question. Let's see the second question. The second question says that we have observed that sigmoid neuron has become saturated. What might be the possible value of output of this neuron? Okay. So sigmoid, there is some. So we are asking for something called sigmoid neuron, and we are said that this is saturated. Well, what does this even mean, right? So I hope you remember sigmoid activation function, right? Sigmoid activation, sigmoid of x, right? So what was this? I hope you remember this was 1 plus e raised to minus w transpose x, right? Something like this. So what does saturation mean? In general, this term is generally used very widely, and somehow it has gained this meaning that saturation is a point. So whenever something like saturation, whenever you hear this word saturation, right? Uh, when if you remember, when you mix your sugar, let's say you put some sugar in the water and mix it, you say that the sugar is saturated in the water, right? Saturation, what does it mean? It means that sugar is no more visible, and I think even if you even if you mix for some more time, you won't see any significant change in the water. It will look as it is. Okay. So that is what saturation means. Saturation basically means that there is no more change that you are saying. It is more or less constant, something like that. Well, what does it mean in this context, right? In the context of sigmoid activation function. So let us draw the sigmoid activation function, right? So what does it look like? Uh, okay, so I think something like this, right? So this is your 0, this is your 1. I hope you will agree that sigmoid activation function takes values between 0 and 1. Why is that? This is because so this exponential function is always positive. That is clear. So we are adding something positive to 1. Okay. So it has to be this term has to be greater than or equal to 1, right? Now, having said that, we are dividing 1 with something that is greater than or equal to 1, right? So it has to be less than 1, right? So you can see that, that way, sigmoid activation will always be between 0 and 1, right? And how does it look like? It looks something like this, right? Sorry, something like this. You do this and then something like this, right? Yeah. So this is how sigmoid activation generally looks like. So so can you see some point which is, where you can say that, sigmoid function is saturated or something? Well, if you look closely, this positive part of this graph, right? This is your 1. So this is 1. So it asymptotically, this function asymptotically touches 1. What does it mean? That it means that when x is equal to plus infinity, it will touch 1. Well, plus infinity is not really a number, so I mean it doesn't make sense. That is why we say that this function touches 1 asymptotically, at infinity. But what we can see is that as soon as we move after certain point, let's say here, this function is not changing a lot, right? It is more or less constant. It is going closer towards 1, but it is not touching 1. Hence it is, in some sense, we are not able to see a lot of change in this function at in this region, right? Same is there is same is the case on the negative side as well. So this is your 0 function, right? This is your 0, right? And this function is, going, it will again touch 0 asymptotically at minus infinity, right? So because of that same reason, you can see that after some point, it has a very less value, right? But it is not touching 0, but it is not changing a lot either. Okay. So I mean, you can think of, let's say this point was, let's say 0.0001, and this point is, let's say what, 0. So let's say this was 0.0, this thing 0.000, let's say 8, something like this. These 2 points, though they have different values, they are, very close to each other. They are they are close by order of 10 raised to minus 4. So more or less they are the same values. Okay. So this is another saturation point. So there are two saturation regions in sigmoid function. One is this and one is this, right? One on the positive side and one on the negative side, right? So this is fine. So now what are we? So if we have understood this, we can go forward, right? So we are asked that we have observed that the sigmoid neuron has become saturated. What does it mean? So it is giving some value here or some value here. Okay. What might be the possible value of the output at this neuron? Well, So I mean, from the explanation that I just said, it is clear that if it is saturated, it has to give either something which is very close to 1, or it has to give something which is very close to 0. Okay. So what are the options that is given to us? So the first option, A option, is 0.94. Well, this is a very really close to 1. Okay. B option is 0.04. This is again very close to 0 on the negative side, right? The C option is 0.65. Well, this is, like in the somewhere in the midway, right? And D option is 0.35, So, I mean, from, we can clearly see that, this option and this option are correct options. Why? Because 0.94 has to be, if the output is 0.94, then maybe it has to be somewhere here, right? Or something like that. That means that, it is not going to change a lot now, right? Similarly, if the value is 0.04, let's say some point here, it again means that, it has come to a point after which it won't change a lot. So A and B options are correct. These two points are, you may be somewhere in the middle, right? Somewhere here or somewhere here. I mean, so they still have a scope to change a lot, right? So I mean, this point can, this point has still a long way to go to 0. This point has a long way to go to uh, the negative side and things like that. So I hope you can see that saturation just means that either the value is very close to 1 or 0, or whatever the asymptotes are. Okay. Or if you have any question, you can just unmute yourself. Okay. If something is not clear, then just ask. Okay. If I were you, I would have, I won't have cared what other people think. I would have just asked question if that worries you. Okay.
I just
So
wanted
come.
to clarify, the sigmoid
Yeah.
function is 1 by 1 plus e to the power of minus x, or is it you have a transpose also?
Oh, yeah, yeah. So you are correct. So I was writing this in terms of the activation function, but you are right. The sigmoid function is actually this 1 plus e raised to minus x. In fact, this function that I have drawn here is actually that thing itself. Okay. But let's say, you are applying this in a neural network or something. So this x won't be x. I mean, this would become W transpose x, right? So you are getting something from the previous layer, let's say x. You apply a linear transformation, which will make it W transpose x. Then you take sigmoid of it, right? So I was saying it from that point of view, but you are also, I mean, you are correct. You are absolutely correct. This is what it should be. Okay.
Okay, thank you.
Right. Yeah, but I hope you can see that, this won't change anything. I mean, the same argument will go for W transpose X as well, because what will happen if you, instead of minus X, you take minus W transpose X? What will happen is, okay, you might observe something like this. You can see a change in the slope in there, but you will still see some sort of saturation, right? That is inherent. So the arguments that I just gave will still follow. What you will see is, maybe the transition is a bit different, but the saturation regions will remain as it is. Okay. Okay. So let's move forward. Here is the third question. Okay. What is the third question? Suppose we have been given the following neural network. Okay, so let me draw this network first. There are three input layers. There are two hidden layers, so there are two neurons in the first hidden layer, one hidden neuron in the second hidden layer, and one output neuron. Okay, something like this. And the connection between them is as follows. So this is connected like this. Right? So this is like this. Okay. This is connected like this, standard way, and something like this. Okay. Now, if the edges from hidden layer 1 to hidden layer 2 are W1 and W2, so we are saying this is W1, this is W2, all right. Which of the following are possible values of gradient of W1, gradient of W2, given that sigmoid is being used as an activation function? So we are being asked that what will be the value of, what are the possible values of gradient of W1 and gradient of W2. Okay. And what are we given? We are given that, this, the activation function, this is sigmoid. Okay. This we know. Okay. All right. Okay, cool. So let us see. So just looking at the question, it immediately it is not clear, right? That why should something like this? Why should we be able to comment anything on this grade on these gradients? It is not exactly clear. So whenever something is not clear, try to write maths. Okay. Let us see. Let us see what happens, right? So in feed-forward networks, we saw something called chain rule and backpropagation algorithm. Let us use that, right, to calculate each of these terms. Okay, gradient of W1 and gradient of W2. Okay, so let's see what is gradient of W1. What is gradient of W1? This has to be gradient of the loss function, right, with respect to W1, right? I hope this is clear. This is what we will, so when we run, so let me just zoom in here and write it down. The way we will update W1 is like this, right? W1, let's say at I plus 1th iteration is W1 at ith iteration minus alpha times gradient with respect to W1 L of W1 at W1 at ith extent, something like this, right? So this thing is what this is del L of W1 by del W1, right? This is what it is. So this is what we term as gradient with respect to W. This is nothing else. Okay, just to recall that how we calculated gradients and all those stuff, right? Okay. Now we take help of backpropagation algorithm, or in other words, we take help of the chain rule, right? So what does the chain rule tell us? The chain rule tells us that to calculate this entire gradient, you can uh, split it in different parts whose gradients are easy to compute. That is what it says. Okay, so okay, just remember that this will give you some y, right? And using some y, you will calculate L, right? Always make this graph so that it becomes clear to how to write this gradient, right? So start with L. You know how to calculate its gradient with respect to y, right? That is easier. So let us take that thing, del L by del y. Well, now if I have done this, then I have to do del y by del w1. So in some sense, this is very hand wavy and incorrect, but you can think that these two are getting cancelled. Okay. However, this term is easier to calculate than this term, so we are taking help of it. Okay. So now this, can we calculate this thing? Well, again, take help of the chain rule and move forward and move backward. Okay. So let's say, so it is given in this figure that nothing is given, right? So maybe let's call it, so this is first layer, second layer, third layer, right? So maybe let's call it activation of third A3. Okay. So I think we can calculate del y by del A3, right? That is easier to calculate, something like that, right? So I think we can do that. So what will that become? Uh, okay, so what is the terminology that we are using? So H is being used to denote the output of the layer, right? Okay, so let us make it H3. I'm sorry, so let us make it H3. H3 is what? Sigmoid of, let's say, A3, okay? Maybe A3 is the output here, okay? Something like this. So what will this become? Uh, Using chain rule, this can further be split as del y by del h3. Okay, now I can use del h3, uh, gradient of h3 with respect to a3, because they are directly related using this equation, right? So what will this become? Del h3 by del a3, right? And lastly, what we can do is del a3 by del W1, right? This is easier. So I am just applying chain rule. If this was confusing, the way I understand back propagation and this chain rule is, just make the graph of the variables and try to move in the opposite direction. So let's say if I want to calculate this gradient, I will move the graph, I will see the graph in the reverse direction and calculate the gradient. If I want to calculate the gradient of L with respect to W1, I will see what are the variables involved and take keep taking the gradients. I mean, it depends on person to person. For me it is easier to look at it like this. Okay. Okay, so now what is the A3 is the output of this neuron, this particular neuron. Okay, so what will it be? Uh, so if this value is, let's say, some H21 and this is some H22, what will be the output of this thing? Well, it will be, so I mean I am just writing what is the value of A3, right? A3 will be what? W1 times H21, right? W1 times H21 plus W2 times H22, right? W2 times H22. Okay, this is the simple uh, um, multiplication. I mean, how we calculate matrix multiplication, multiplication of weights with the corresponding input, right? From this, what we can see is that, okay, so I'm just making this thing. Del A3 by del W1, what is it? It is simply H21, right? Because this term doesn't depend on W1, so this will cancel out. And in this term it is simply multiplied by h21, so h21 will remain, right? So essentially what this becomes is del L by del Y by del H3, del H3 by del A3 into H21, the value of this, right? So I'm just substituting it here. I hope this is clear. Similarly, what will be the gradient with respect to W2? uh, I hope you will agree that these things will remain as it is, because till here everything is same. However, when we take gradient of del A3, it will be with respect to W2 instead of W1, right? So what I mean to say is that this will be del L by del Y by del H3, del H3 by del A3, and del A3 by del W2. So this was W1, this is W2, right? And what will be that differentiation? Well, this term doesn't depend on so this term doesn't depend on W2, so this will be 0. However, in this term, it is simply multiplied by H22, so the differentiation will be H22 itself. Okay, so this will become what? Del L by del Y by del H3, del H3 by del A3, H22, right? Okay. Now, we also know that we are using sigmoid activations, as we know. Okay, so what are H21 and H22? H21 and H22 are outputs of these two neurons, right? Now we know that from this graph that sigmoid is always between 0 and 1, right? So it is, so any value will be between 0 and 1, right? So it is going to be positive. Okay, so what we know is that, so so these equation and this equation, what we know, H21 comma H22, these are both greater than or equal to 0, that we know, right? Or in particular, this will be in the range of 0 comma 1, because sigmoid has a range between 0 and 1, right? That is fine. So so uh, so what can we say? So basically what we are saying is that these two terms are going to have the same sign. Well, now this term, right? This term that is here and this term that is here, it is common in both the gradients, right? Now, if it is common in both the gradients, so if this term is, so let's call it some common term CT, right? This is del L by del Y by del H3, del H3 by del A3, right? This is the common term. If this is, let's say, if this is greater than or equal to 0, then what can we see? We can see that if this is greater than or equal to 0, right, this term will be greater than equal to 0. This is already positive. So this will also be greater than equal to 0. So, right, though multiplication of two positive quantities is always positive. Similarly, if this is positive, this is also positive, this will also be greater than equal to 0. So we can see that if this term is positive, then gradient of W1 and gradient of W2, both of them will be greater than or equal to 0. Well, what if it is less than 0? If it is less than 0, then this is a negative quantity, this is a positive quantity, right? Similarly, this is a negative quantity, this is again a positive quantity. The multiplication of a positive and a negative is negative, right? So we can say that gradient of W1 times and gradient of W2, these are less than 0, right? This much we can say, right? So we can see that either the gradients are both positive or both of them are negative. The only possible cases are that either both of them are positive or both of them are negative. This much we can see. Can we say anything more than this? Well, no, right? I mean, we don't know anything else about it. But from our analysis, what we saw, we can say that either both of them will be positive or both of them will be negative. So let us look at the options now. So what is the first option? First option is minus 0.1 comma 0.1. B is 1 comma minus 1. C is 2 comma 2. D is minus 1 comma minus 0.1. Well, is this possible? Well, this is not possible at all, right? One of them is negative, one of them is positive. However, we have seen that either both of them will be negative, positive, or both of them will be negative. Well, will this option suffice? Well, this will also not suffice because one is positive, another is negative. Will this option suffice? Well, this will work, right? Because both of them is positive. So this is possible, right? I mean, both of them can be positive, both of them can be true. I don't care what the value is, but both of them should have the same sign. Is this possible? Well, this is again possible, right? Both of them are negative this time, so this will also work. I don't care what the value is, but the sign should be same. That is all I need. Right? So C and D will be the correct options. Okay. So yeah, so these two and these two, C and D will be the correct options.
Is is this does this condition always hold that all there will be the gradients at a layer, there'll be all positive or all negative in a layer?
Well, it depends on the architecture. Okay.
Okay.
In particular, here in this architecture, it turned out that there was a common term here and here, right? And I mean, I hope you can see that if the architecture was different, let's say, I mean, if let's say there was one skip connection, something like this, right? This won't hold anymore, right? I mean, things will become complicated because the architecture was such that the gradients of both these terms had a common term and something which is always positive. It turned out that either both of them will be positive or both of them will be negative. But this might not always be the case. It can be different as well, right? Okay. So so I hope this was clear. If you have any other doubts, you can always unmute yourself, right? So let's see the next question. So this is the fourth question. What is the fourth question? Which of the following problem makes training a neural network harder while using sigmoid as the activation function? Okay, let's see. Uh, okay, so basically we are asked that if we are training a neural network, right? What properties of sigmoid activation function uh, are not desirable in some sense, right? Okay, so let us see the options. Okay, A is something called saturation that we just saw, right? Is saturation desired? Well, no, right? I mean, saturation is not desired. Well, what is the B option? Non-differentiable at zero. C option is computationally expensive. Computationally expensive. What is the D option? D option is range of the output is 0 comma 1. Okay. So which of these properties? So first of all, let's see, are all of these properties correct? Uh, well, for the first option, what do you think? Is this undesirable? Well, okay, sorry. Yeah. So saturation is undesirable, right? I mean, we just saw it here that sat. So okay, why saturation? So we saw what is saturation, but we didn't see why it is undesirable. So think of it like this, that because of saturation, I mean, saturation in some sense restricts your learning, right? Basically, what we are saying here in saturation is that the values won't change a lot. Okay, if the values are not changing a lot, what does that mean? It means that the gradient will be very small, right? Gradient is rate of change, right? And if you are not changing at all, it means that your gradient is very small, right? And if your gradient is very small, what does that mean? It means that this term is very small, right? If this term is small, what does that mean? That you are not learning anything. You are basically saying that theta I plus 1 is equal to theta I. That means you have converged, right? That is why saturation is something that is not desired. Okay. So I hope that was clear. If not, please ask. I will explain again. Okay, in some details. But since I have already explained saturation, I think that that much explanation would be clear. Okay. So saturation is not desired. Hence, it is a correct option for this question. Second option is non-differentiable at zero. Oh well, is it non-differentiable at zero? So here is your sigmoid function. This is your one, right? And we saw that it looks something like this, right? Well, I mean, it is differentiable at zero, right? I mean, uh, like, let's say, I mean, 1 upon 1 plus e raised to minus x. This is a continuous function, okay? There is no issue with it. If a function is continuous everywhere, then it is differentiable, right? And there is no issue. Hence, I mean, this will work, right? I mean, by from the graph at least you can see directly, right? There is no issue. So this statement itself is wrong. This is a wrong statement, hence it is not a correct option. Third is it is computationally expensive. Well, uh, so do you know how exponential is calculated? E raised to x. This is generally some people use something called power series. 1 plus x square by 2 factorial plus x cubed by 3 factorial plus till so on, right? So this is summation x raised to n by n factorial. N goes from 0 to infinity, right? So calculating this is actually expensive because you have to sum for very large you have to do this summation for very large term. If you want to look it up, look at uh, fast exponential fast exponentiation. So there is something called fast exponential that people use to calculate the exponential. So I hope you will agree that e uh, this so e is like pi. Okay, I mean, since pi is also irrational, so it is an irrational number. Similarly, e is also an irrational number. Okay, to calculate e raised to something, you need to use this formula. And this formula has to be computed for a large sum. Since this has to go to infinity, practically we cannot go to infinity. So let's say we will go to a large number like 1,000 or 10,000, something like that. And hence calculating this sum will be computationally expensive. And we can see that calculating so calculating sigmoid requires calculating an exponential term. Hence, whenever there is a term that requires calculation of exponential function, it is computationally expensive in general. Okay, so because of for this reason, it is also computationally expensive, right? Range of the output is 0 to 1. Well, is this correct statement? Well, yeah, I mean, the range of sigmoid function is always between 0 and 1, right? However, is this undesirable? Well, it is undesirable. If you have, maybe if in the lectures, if you saw something called vanishing gradients. What is vanishing gradients? In simple terms, it is a very fancy term, but let us, I mean, if you want to understand it very in simple terms, let us consider the following. So let's say that you want to calculate a number n, which is equal to a into b into c into d into, let's say, something like this. Let's say a into b into c into e, something simple, right? So a, b, c, d, e are all numbers, and n is the product of all these numbers, right? And in addition, I will say that these a, b, c, d, and e, all these belong to 0, comma 1. I mean, these are numbers that are between 0 and 1. Okay. So what do you think? What will be the product? Will the product be greater than 0, greater than 1, or will it be very small than 0? I mean, what would you expect? Well, I mean, so let's say there is a number x, okay? If you multiply it by number a, yeah, it will be very small, as correctly pointed out. So if this will be less than x, if a is less than 1, and greater than or equal to 0, it will be greater than x if a is greater than 1. I should call mod of a, right? Mod of a, something like that. Which is basically saying that it is something very simple, right? I mean, so let's say you had 100, okay? If you multiply 100 by 0.1, it gives you what, 10, which is less than 100. If you multiply it by 1.1, it gives you 110, which is greater than 100. Something very similar. This is what I'm saying. So basically, so having said that, what I'm saying is that if you are multiplying a lot of small numbers, the multiplication of all these small numbers will be an even smaller number. Okay. And hence this will, this will be very small. And since this is very, so, okay, so this was a general statement. This is true anywhere, right? In gradient descent, when we are applying gradient descent, okay, you can always see the term. So like here, we saw something called del y, del h3 by del a3, something like this, right? So assume that uh, so let's say your gradients are like this now. So let's say this is some del l by some del w, okay, and these terms are like del uh, what and these terms are like your sigmoid function, something like this. Now we know that each of these sigmoid function is between 0 and 1, right? Each of these sub function is between 0 and 1, as we can see from the graph as well, right? Because of that, each of them are small, and multiplication of a large number of small numbers is very small, okay? Hence this gradient is very small. And again, as we just saw, if your gradients are very small, then essentially you are not learning anything, right? If your gradients are very small, this term is not making any contribution, hence you are not learning anything, right? So for that reason, uh, range of the out because the range of the output being 0, 1 is also an issue. So this is also a correct option. Okay. So these three options, A, C, D, will be the correct options. If you have any questions, just ask it out. Okay. Okay. So moving forward, fifth question. What are the problems associated with tan HX? Okay. Problems with tan H, tan hyperbolic X, right? So what are the problems associated with this quantity, this function? How does the tan hx function look like? Well, if I have to draw a graph, so something like this, okay? Something like this, right? And on an x-axis, right? So let's say this is plus 1, this is minus 1. I think it goes something like this. It crosses the this thing and it goes like this, or something like this. Okay. So this is how a tan hx function looks like. I think the expression for this is something like e raised to x plus e raised to minus x upon e raised to h minus e raised to minus something like this. I don't remember exactly, but it has something. But I remember the graph. This is how the graph looks like. Okay. So well, let us look at the options. What is the first option? It is not zero centered. It not zero centered. What do we mean by zero centering? It means that on the y-axis, okay, on the y-axis, is it symmetric about zero? Well, it is, right, because I mean the same part goes here, and in some sense a reflection goes here, right? I mean zero is in kind of in the middle of the y-axis, the two halves of the y-axis, right? So if you see it from, let's say, this way, okay, so this is the first half, this is the second half, and zero is coming in middle. So it is zero centered, right? So this is not a correct option because it is saying that it is not zero centered. It is zero centered. Okay. Was sigmoid zero centered? Well, no, right? Sigmoid wasn't zero centered because this was the function. If I had to see two parts, this was the first part, this was the second part, this was the middle, which was 0.5. So it was 0.5 centered, but it was not zero centered, right? So A is not the correct option here. Okay, so what is the B option? Computationally expensive. Computationally expensive. Is it computationally expensive? Well, again, it requires calculation of lot of exponentials, right? So indeed, it is computationally expensive. Whenever you see a term, a loss function which contains exponential terms, it will be computationally expensive. So this is a correct option, right? This is an undesired property. This is a problem with tan hx. C part, saturation. Do we observe saturation here in this graph? Okay, so I think I mistook the spelling. Uh, something. Saturation. Do we observe saturation? Well, indeed. I mean, this part and this part is very similar to the sigmoid function, right? And indeed, you can see that asymptotically it will touch plus one, but it is going closer and closer, but it is not never touching it. Similarly, on the negative side, it is going closer to minus one and closer and closer, but it is not exactly touching it. So I mean, these are the regions where they will remain more or less constant. Okay, they will increase, but they will increase by very little, and hence it will look like they are almost constant. So they do have saturation points, and hence saturation is an issue. Okay, what is the fourth option? D option, non-differentiable at zero. Non-differentiable at Is it non-differentiable at zero? Well, I mean, so see, this is continuous, all of them are continuous, and the division is also continuous because I mean exponentials are I mean they are nice functions because they don't go to zero. Okay, hence I mean even from the graph you can see that it is a continuous graph. At each point it is continuous, so it will be differentiable at zero as right. So this is a this is this is an incorrect option. Hence, it won't be. So this is not. So B and C are the correct options. These are actually problems with the tan H activation function. So if you have any doubt, or I mean if I move very fast, I mean this was similar to the previous question, but uh, instead of asking for uh, sigmoid, we were talking about tan H function. Okay, if you have any doubt, you can ask. Okay.
Is it that we use tan x or tan h only when we have a range which is required between minus 1 and 1, or when is it preferred compared to a sigmoid?
Right. So yeah. So okay. So the problem with sigmoid, as we saw, was that it is so one problem is that it is not zero centered. Okay. Uh, can you see that? I mean,
Yes, yes, yes.
okay, just a second. I am not able to see the teams on my browser. Uh, just a second. Something is happening. Are you able to see my uh, are you able to see my video and all these things?
Yes, yes, it's visible.
For some reason I am not able to see yours. It suddenly it snapped something. Uh, okay, just a second. What is happening? Just a second. Let me try something. Control Shift T.
Maybe you can
Yeah.
stop
Okay.
sharing and then maybe you get it
Yeah.
something.
Yeah. No. No. I don't know how, but I think some Mac has some issue with Teams. And now it is visible. All right. Okay. Yeah. Sorry. Sorry. Yeah. So your question was, sorry, I forgot. Can you
My
repeat your
question was,
question?
when is TANH preferred? The two differences are that, TANH is zero-centered, whereas sigmoid is not. And the values of TANH is -1 to 1, whereas sigmoid is 0, 1. So when we want a wider range of values, that's when we use TANH, or when is this preferred?
Well, okay. So to answer your question, the one thing that you said that the range is just 0, 1 here, and the range here is +1 to -1. Is that something that gives an edge to sigmoid, edge to tangents? Well, not necessarily, because let's say what I a simple trick that I can do is, instead of using sigmoid, okay, naively I will use 2 times sigmoid. Okay, what will happen then? So you will observe that this function which was between 0 1 will now become between 0 and 2. Okay, I mean, this will be the something like this, and something like this will come out if you use 2 times the sigmoid function as your activation function, right? So width has nothing to do with it. I mean, you can always increase the width of your uh, uh, function by multiplying it with some scalar, right? I hope you can see that. I mean, and most more like most even if I have to, so let me do this thing once. Okay, so let me draw this thing. Okay, uh, so this is your one. This is your -1. The sigmoid function looks something like this. Okay, and your tan h function looks something like this. Okay, something like this. Okay, something like this. All right. So if I have to, let's say, make if you ask me to convert this sigmoid to look like tan h, what I can do is I will take my sigmoid function, okay, multiply it by 2, okay, and subtract 1 from it. So what will it look like? So multiplying it with 2 will make it go from 0 to 2, right? I mean, this is what 2 will look like. Now I am subtracting 1 from it. So this entire curve that was going till some 2 here, okay, it will shift down by 1, right? So I hope you will see that, if I have to make an equivalent diagram, it will look something like this. So this red curve is 2 times sigmoid -1. This is your tan h, and this is just your simple sigmoid. So I hope you can see that you can always modify your sigmoid function to look to cover some range, arbitrary range that you want. Okay, I hope that is clear. So That is not the reason. However, there are some reasons where because of which tan H is preferred. Okay, so the first thing that is there is that tan H has stronger gradients. Stronger gradients. Why is that? Well, since tan H is centered around zero, right? Since this is centered around zero, the derivatives are higher. How can you see that? So you can do this as an exercise. Do this del by del x of tan hx, okay, tan h, okay, and del by del x of sigmoid of x, okay. Calculate these two at x equal to 0, okay, x equal to 0. You will observe that this value is greater than this thing, okay. That is something which is desired. Why is it desired? Higher gradients mean that you can change your gradients a lot by being in this range. That is all it means. So in that sense, it does help. Okay, I mean, if you basically, so what I mean to say is the following, right? Sigmoid function has a very steep curve. Okay, I mean, okay, let me use this sigmoid function. Okay, I will draw it here. Sigmoid function has a very steep curve in the sense that it is almost constant. It almost increases and then it becomes constant. Something like this. Because of this, there is a very small range to learn something. If you move a bit this side or if you move a bit this side, it will the gradients will become zero very quickly. Okay, whereas for tan H, this region, it is also similar to this, but it has a relatively bigger slope. Okay, so it has a bigger range, and it allows so it's not like that if you are here, if you may move a little bit left, or if you are here, if you move a little bit right, you will start encountering zero gradients. That will not happen with tan H. However, with sigmoid, it will happen because it has a very small range of transition. Okay, so because of this reason, because of the gradient properties of the gradient of these two functions, tan H is generally more preferred than sigmoid. Okay, that is the basic reason. Was that clear, or I don't know, was
Yes,
I able to
yes,
explain
yes.
it?
Thank you. Thank you.
Yeah. Okay, so this was fifth question. Okay, so still have some time. Sixth question, what is it? So sixth question is saying that we observe that in the following neural network with ReLU as the activation function, weights in the first layer uh, weights in the first hidden layer and input layer are not getting updated. Choose the correct option for the value of bias B going to second hidden layer. Okay, right. So okay, so here is the network that is given to us. Three here, again three here, two here, and one here. Okay, so they are connected as usual. Okay, no, so this is a bias term, so this is only connected to these two. This is connected like this. uh this is connected here, this is connected here. Okay, so this is connected here, something like this. All right. Someone was trying to come in. Okay. Okay, so this is some network. This is hidden layer 1, this is hidden layer 2, this is input layer, and this is output layer. Okay, so we are given this network. What we have said is that uh, we have said that weights in the first hidden layer. So the first hidden layer is this one. Okay, and the input layer and this layer are not getting updated. Okay, so what are we told that here and here the weights are not changing a lot. This is what we are told. Okay, we are also told that we are using a ReLU activation. Okay, so ReLU activation. Okay, so we are asked that what is the value of this bias term that is going in the second hidden layer. So let me just maybe measure it out. So we are asked that what is the value of this thing. Well, let us. Okay, I hope from till now you will have understood that whenever we are asked that something is not changing or something is staying constant or some saturation is there, it is always due to the activation function, right? As we saw with here we saw it with tan h, earlier we saw it with sigmoid. So whenever some question like this comes, the first thing is you should draw perhaps you should draw the activation function itself. So how does the ReLU function looks like? It is zero till in the on the negative side. On the positive side, it is a constant y equal to x, right? This is how ReLU function looks like. Okay, is there a saturation point here? Well, there is a clear saturation point in ReLU, right? Why is it saturation point? Because it is zero constantly. I mean, at least in sigmoid and tan H, it was changing by a bit. However, we can see here in this. Okay, okay. Here we are seeing that so I was saying that in sigmoid and tannage we were at least able to see some change. There it wasn't constant completely. So this region that we were saying was it is increasing, but it is changing a bit, changing by a very less amount. So it is almost like it is as if it is not changing. However, in ReLU it is clear that it is totally zero on the negative side. So this is a saturation point. So this must have something to do with this this observation that you are not able to observe any changes in your weights. Okay, so let's write it down. So what is the del by del x of ReLU function? Let's call it r of x. So when x is greater than or equal to 0, I mean on this part it is y equal to x, right? So what is the differentiation of y with respect to x? It's just 1, right? So this will be 1. If x is less than 0, well, when x is less than 0, it is always 0. So there is no change, hence the derivative will be 0, right? So this is 0. So we can see that, there is some region which is x less than 0, this region, where the gradients are becoming 0. And we know that when the gradients are becoming 0, always go back to, that equation that wt plus 1 is equal to wt minus alpha times gradient with respect to wl at wt. Whenever you see that something is not changing, it must be that this term is becoming 0. And in case of ReLU function, we are seeing that, this part that we can see, this part actually tells you that the gradient is becoming 0, and hence this has to do something with it. So let's see. So we know that this is not changing, this is not changing. All right. Uh, so let us see at this point. Okay. So for these W's, right? For these W's, what should be the case? So we know that it is not changing, right? Okay. So what does that mean? Let's write it down. I mean, whenever we don't know anything, just write things down. So let's say this is W1, this is W2, okay? And let's say this is some bias B, right? So what will be the input that is going here? This should be W1 times, let's say this is H1, this is H2. I mean, I'm just using some arbitrary terms. So the thing that should be going here should be what? W1 times H1 plus W2 times H2 plus the bias term B, right? This should be what must be going inside, right? Now we know that this has to go from, okay, so let me write it down, W1 H1 plus W2 H2 plus bias term, right? We know that this is what it is happening. Now we also know that this has to go through the ReLU function, right? Because we are using ReLU function, this is what has to go. I mean, this is what the activation would be, right? Now, if this is the activation, and we know that W1 is not changing, W2 is not changing, this means that the gradient of this with respect to W1 and things like that should be 0. W1 or W2 should be 0. Now when is that possible? Well, this is possible when this entire term, when x is less than 0, right? So this entire term has to be less than 0. When is it possible that this entire term is less than 0? So W1 H1 plus W2 H2 plus B, right? This has to be less than 0. When is it possible? Well, it is possible when one possible case is when B is much less than 0. Okay. So I mean, let's say for argument's sake, let's say this is equal to some quantity 10. This is equal to some quantity, let's say 100, and I'm saying that B is, well, this is minus 1000. Okay, if I add these things, these are always less than 0, right? So whatever the value will be there, this will be always less than 0, and when I apply a value to it, this will become 0, right? And hence when I calculate the this gradients, I hope you will agree that this will be 0 because you are lying in this region. Hence when you're lying in this region, this is a negative region, and your value is constantly 0. Hence the gradient will always be 0. Hence you are not getting any gradients to learn, so W1 W2 are staying constant. So uh, so is that clear that because this term is less than 0, the ReLU is 0, right? And since the ReLU is 0, the gradients are also 0, right? So I don't know if it was clear or not. If you didn't understand it, then let me know. So the reason is B must be very small. And from the given options, if I see, so first option is B is equal to plus 20. Well, this is greater than 0, so there is no chance that this is a possible reason, right? What is the second option? B is equal to 0. Well, B is equal to 0 is saying that these things are just you're adding 0, so this thing doesn't contribute. Well, that is also not the case, right? What is the C part? C part is B is equal to minus 0.4. Good, this is negative. And D part is B is equal to minus 50. Well, we need B much less than 0. So this is like very close to 0, right? I mean, this doesn't look like a major, very less number. So this is not the case. So D option is perhaps the correct option, right? So B is equal to minus 15 is the correct answer. So let me know if I wasn't clear or there was some doubt. Okay. Uh, because I moved a bit fast, so I don't know if I was clear or I was making sense of it. Okay. So what is the seventh question? We tr- Seventh question is, we train a feed forward neural network with tan HX as activation function and observe that the neurons are getting saturated. Okay, now we know what saturation is. Okay, we have seen it multiple times. So we are seeing that tan HX is being used, tan H is being used, and saturation is also being observed. Saturation. All right. What are the possible causes for this phenomenon? So let us see the options. Weights are initialized to very high values. Weights are initialized with high uh, values. Okay. B option is weights are initialized with very low values. Low values. Okay. C option is weights are initialized to 0. Weights are initialized to with 0. Okay. So and D is all of these, right? D is all of the. So, well, let us look at the tan HX loss function. I mean, let me draw it again. Something like this, something like this. We know that it goes from here to here, right? Now, let's see. If you initialize your weights to be very high, with very high values, right? What does it mean? It means that, you are multiplying something very large to a number. That means that your output should be very large, right? So it should be on this side of the axis, right? If you are having something on this side of your axis, well, you can see that tan HX for very high values saturates, right? I mean, that is clear that if you are taking something very large and then you are applying tan h function on top of it, it means that you will be in the saturation region, right? So this is perhaps this is a valid reason for the neurons getting saturated. So this is a correct option. Now what happens if you initialize with very less values? If you initialize something with very less values, something in this region, right, it again means that you are now on the negative side of the saturation region. You will again saturate, but on the negative side, on the -1 side. But you are still saturating because you are on the negative, very negative part of the x-axis. If you take tan h of it, you will be again in the saturation region, right? So again this is an issue. And the third option is weights are initialized to zero. Well, if you initialize weights to be zero, right, think about it. If you initialize weights to be zero, so let's say you are using some w transpose x plus b type of, let's say, ignore the bias term for now, ignore this bias term. So you have w transpose x and you are saying w transpose x is zero. So you're saying that basically this is equal to zero, right? So whatever your input is, right, you're saying that your output is zero, right? And if your output is zero, well, what would this mean? This would mean that so it's like you are saying that whatever your input is, your output is always zero, right? And because of this reason, I mean, you will always see the output is zero again and again, right? I mean, there will won't be any learning because of this. I hope I am able to convey my point. So if you initialize your weights with zero, whatever you multiply it with, it will always become zero. And hence you will always see your output to be zero, right? And because of that, you will see that your weights are not updating because you are saying that always it is zero and there is no learning that is being involved. So that is also a possible reason, right? So B option was correct, and C option is also correct, right? That if you initialize it with zero, then also it is an issue. So basically, A, B, C are correct options, and hence all of the above. So all these three options are correct. Okay. Let me know if this was not clear. So so Manaswini is saying why not B equal to minus 0.4. So can you more clarify it? I didn't get your point.
Yeah, so in the previous question, like B should be very small, right? So minus point 0.4,
No, no.
why not?
Yeah, so B should not be very small. B should be very negative. Okay. Uh, so what B being very small means that B minus. So I mean, so this does not mean B is very small. Okay, this means that B is very negative. Okay, so this is your x-axis, this is your zero, this is, let's say, plus infinity, this is minus infinity. What I'm saying is that B should be much less than zero. Okay, so this should be very less than zero. It should be minus infinity or a very small number, right? Minus 15, I hope you will agree that it is a very small number compared to these other options
Yeah,
that are given
got,
to us.
got it, got it. Thank you.
Right? Yeah. So this was the seventh question. We are running out of time again. Let me try to quickly do all the questions. So there is this eighth question. We train a feed-forward neural network and observe that the weights learned are equal for a single neuron. Okay. What are the possible causes of this problem? Okay. So what is being said? Uh, we are train a we're training. Okay, right. So this is coming from the symmetry breaking problem, right? Yeah. So let us see. So what are we given? That there is a feed forward network, okay, and we are observing that the weights uh, are equal is what we are being what we are given for a single neuron. So the structure is like there is a some neuron, okay. So there are some weights that are coming in W1, W2, W3, W4, something like this. We are saying that all of these weights are equal, okay. What are the possible reasons for it? Is the question. So are you aware of this symmetry breaking problem or? do I don't know. So because I have less time, if you already know, then maybe I will just skip to that part. Or
Can you quickly explain it with respect to this question?
okay, so all right, so okay, so mm, let me think of a better way to explain this thing. uh, okay, all right, so let me explain that thing. I'm just seeing in the slides if it was covered or not, just to be sure. Uh, I don't know, was it covered in this thing or not? Was it covered in the lectures? I don't know.
Actually, in the slides, I did not find much from it. But I did find these two things that, it should not be initialized to equal values and it should not be initialized to zero. And that's why C and D are correct. But the term, anyways, if we're
Mhm.
short of time, it's okay. I'll look it up or something.
Uh, okay. So let me try to explain it. Uh, okay. Nonetheless, maybe I will do it anyway. So, so there are somewhat how many options? Okay. So, right. So, okay. So let me cover that topic, and maybe that will help you, to explain this. That will make things more clear. Okay. So, so let us think of a network, right? So let's say that there are two inputs. Okay, I can take it as many inputs. For example, let's say there are three, four middle layers, and there is one output thing. Okay, something like this, right? Uh, so I hope you will agree that this is how they are connected. Something like this is there. All right, something like this. Okay. All right. So what happens if if you initialize all your weights with 0? Okay, so let us name it. This is x1, this is x2. All right, so let's say that the input here that goes is a11, that goes here is a12, a13, a14, and so on. Okay, something like that. The output is some h11, h12, h13, h14, something like that. And this is, let's say, a21, and the output is some x21, something like that. Okay, so we are saying, so what is the expression for a11? A11 is what will be w11 times x1. So the weight, this w11 times this input w11 times x1 plus w12 times x2, right? This is how it would be. Similarly, what will be a12? A12 will be what? W21 x1 plus W22 times x2, something like this, right? I hope this is clear. Now we are saying that the weights are being initialized with 0. Let's see what is the effect of initializing weights with 0. If the weights are 0, it means that this is 0, this is 0, this is 0, this is 0, right? So this means that this entire term is 0, this entire term is 0, hence these two terms are also 0, right? So a11 will be equal to a12 will be equal to 0, right? I hope you will agree with that. And since this is the, uh, was there any question?
It's clear.
Right? Okay. So if A11 and A12 are equal to 0, what are H11 and H12? H11 and H12 are out, like if I apply some sigmoid, some activation function sigma on A11, I get H11, right? If I apply the same activation function on A12, I get H12, right? So that means that H11, since A11 and A12 are both 0, right? H11 should also be equal to H12, right? I mean, this is clear, right? I hope this is clear. So
Yes.
now let us see what is the gradient of W11, right? So this W11 that we saw here, what is the gradient for that? This will be equal to, I will just apply the chain rule, right? So let's say this is some y, and this output, so this output some y, and some loss is calculated. So if I go forward in backward direction, what will it become? It become del L by, I have to take it with del y, okay? Then del y with respect to what, the previous thing that comes here is h11, right, with w1. So del y by del h11, then del h11 with respect to del a11, because a11 is after applying the sigmoid function, and after that del a11 by del x1, right? And what is this? Del a1 by del x1 is what? Uh, Sorry, del w11. This will be just x1, right? So I mean, this will become what? Del L by del y by del h11, del h11 by del a11 times x1, right? This is what it will become. I hope this is clear. Similarly, gradient of w12, this the second weight that we saw here. What will that become? This will become del L by, I mean, I will just write it down, okay, directly. Del L, this will become del Y by del H12, okay, del H12, sorry, it's 100, it's not 100 and it's 12. Del H12 by del A12 times X1, right? This is what it will become. But however, we know that, H11 is equal to H12 now, right? And we also know that, uh, you know, uh, A11 is equal to A12, right? So because of this reason, what will happen is that, this thing is equal to this thing is equal to this thing is equal to this thing, right? So because of this, this term and this term, these are same, right? I hope you can see that, right? This h11 is was equal to h12, so this term and this term are same, right? A11 was equal to a12, so del a11 del a12, this will be the same, and h1 h12 are same. These two terms are always the same. So what I'm saying is that this term and this term is same. Now it is multiplied, both are multiplied by x1. So essentially what is happening is that gradient with respect to w11 is equal to gradient with respect to w12. This is what I'm saying, right? I mean, I hope you can see that. So both the weights are getting same update, and remain, and hence they will remain equal, right? Uh, is this clear? By
Yes,
initializing your weights with
yes.
zero, makes it this thing. I mean, the way I proved it for W11 and W12, right? You can prove it similarly for W21, W22, and all the rest of the weights that are there. It will be the same story. Okay. So one option that is correct is weights are initialized to zero. Okay. Since weights are initialized to zero, this works out. Okay. Is it necessary that weights have to be initialized with zero? Well, no, right? I mean, even if so, I mean, weights all being initialized to zero is a special case of all the weights being equal. Just that in this case, since all the weights were equal, but they were equal to zero as well. But if the weights are all equal, right, then also the same logic will follow through. I mean, you can see that, so let's say if W11 and W12 are equal to, let's say, some constant C, right? This will become Cx1 plus Cx2. Similarly, this will become Cx1 plus some Cx2, right? This is what it will become, right? Well, again, A11 and A12 will be equal. Both of them are equal to Cx1 plus Cx2, right? And hence this will follow. It is just that it won't be equal to zero. So this won't happen. But H11 and H12 will again be equal, because they are just applied. We are just applying a activation function on top of A11 and A12. And hence, because both of them are same, these terms will again be equal, and x1 and x1 is always equal, right? So because of this reason, the same arguments that I said for both of them being equal to zero will follow for both of them will equal to some constant c. Okay, is that clear, or am I not clear? Maybe I don't know.
Yes,
I am just
clear.
saying, yeah, it is clear, right? So the two options that are correct for this is, weights are equal, initialized equally, and weights are 0. These two options will be correct. If you see, this option is a special case of this. It's just that in addition to being equal, they are also equal to 0. Okay, so that is another thing that you can see, right? Okay, so eighth question is done. Okay, so let's see the ninth question. Ninth question is, which of the following is incorrect with respect to batch normalization process? Okay, uh, so what is batch normalization? So maybe I will skip the 10th question because 10th question is really easy. Uh, so you just need to draw the graph and from what we have discussed, I think 10th question should be easy to answer. If you some of you feel that it was tough, then ask. I will do it. But right now I'm thinking that ninth question would be the last question. Okay. So what is batch normalization? Batch norm. So the idea with all this thing is right that we can see that if you initialize it equally, then it's an issue. If initialize it with 0, then it's an issue. Earlier we saw that if you initialize it with high values, then also it's an issue. If you initialize it with low values, then it's an issue. So the I mean there is so I hope you can appreciate, right, that hyperparameters are something which is very crucial to the performance of your network. Now, I mean, one can then, an obvious question that one would ask is there a, simple way to address all of these concerns? Well, batch normalization is one such technique. What it does is that, okay, let's say that, there is some some hidden layer, intermediate hidden layer. There are a lot of hidden layers here and there are a lot of hidden layers here, okay? What batch normalization does is the following, okay? It says that, okay, so at so before this it has to so something like w transpose x is coming in, okay? So let's call it some a, okay? So a particular layer is going to get a as its input, right? What batch normalization does is that it says that, okay, what I will do is the following. Okay, so uh, what was that exact expression? Yeah, so it was something like, you subtract the mean of it. Yeah. So it does something like this. So okay, so it calculates some a dash, which is equal to a minus expected value of a by square root of variance of a. So what is it doing? So I hope you can see that expected value of a, this is like mu of, so this is like mean of a. So how is this expectation calculated? So let's say you have a batch size of b, okay? So you will have your any vector a will have a dimension of, let's say, b cross some mod a, right? Something like that. So along the batch axis it will calculate the expectation. It will take the average, and that is how you calculate your expectation, okay? And similarly you can also calculate your variance uh, using the batch axis of your vector, whatever it is, right? So what we are doing is that we are taking a vector, right, a, we are subtracting its mean and dividing it by its standard deviation. Square root of variance is the standard deviation, right? So in some sense this is nothing but a normalization process, right? So what is the idea behind this? The idea behind this is that we are basically saying that uh, these vectors, these inputs to each of these hidden layers can be very far away. It can be arbitrary. It can be very large values, as we just saw. It can be very low values. It can be 0 or something like that. What we are saying is that, well, first of all, make them normalize all of them. What it means is that make them come closer to some mean, which is this expectation of you. Okay, that is first of all we are saying do that. Okay, then what we say is that, okay, Now we have normalized it, right? Next thing what you do is you do the following, right? You say that some a double prime is equal to some gamma times a dash plus beta times plus some beta, normal beta, right? So it's like we are first normalizing it, okay, and then we are unnormalizing it, okay. And here gamma and beta, these are learnable parameters, learnable. So what we are saying to a network is the following. We are saying that, okay, boss, there are a lot of restrictions on the range of input that we can give to you. What we will do is, we will first normalize the input. Okay, we normalize it, and then we will unnormalize it. But how to unnormalize it is up to you. You learn this gamma and beta parameters. Okay, this scale, whatever, scale your input by whatever amount you want, and then shift it by whatever amount you want, so that it's easier for you to learn from the data. That is what we are seeing. So first normalize it, then unnormalize it. However, leave it to the network on how to unnormalize it. This is what we are seeing. Okay, is this clear? This is what batch normalization broadly is. So I hope you will appreciate it, because I mean, we just saw that there are a lot of restrictions on weight, that if it is zero, then there is an issue. If they are equal, then there is an issue. If it has a large value, then it gets saturated. If it has a very less value, then also it gets saturated. So it's a pain basically. Okay, to avoid this pain, what we are saying is that, what I will do is I will first normalize my inputs. Okay, then I will unnormalize it. However, during unnormalization, I will leave it up to the network itself to, I will leave it up to the network how it wants to unnormalize it. It's up to the network. If the network wants to, not unnormalize it at all, then that's fine. If I mean, it is up to the network will learn whatever it wants. That is why this is kept learnable. So what are the options that are given to us? The first option is we normalize so we are asked the incorrect option. Okay, so the first option is we normalize the output produced at each layer before feeding it to the next layer. So normalize the input, sorry, normalize the output produced at each layer. So this is correct, right? So that we are doing it. So this operation that I just saw was exactly that. So this is a correct option. So this is this is an incorrect option because it is correct. I mean, we are asked incorrect things. Okay, so this is correct. What is the B option? Variance and mean are not learnable. Variance and mean are not learnable. Well, this term that we saw, beta and gamma here, you can interpret gamma as the variance and beta as the mean. Okay, this is what they mean. Well, this is learnable, right? I mean, this is the entire point, right? This is learnable. So this is incorrect, right? This statement is incorrect. Hence, it's a correct option. Okay. What is the third option? Third option is batch normalization leads to better initialization of weights. Leads to better initialization. Well, this is correct, right? This is the entire point of batch normalization, right? I mean, this is why we are doing it. So, I mean, this is a correct statement, so it is a incorrect option. Okay. So, finally, coming to the D option, back propagation can be used after batch normalization. Back propagation can be used. Well, it can be used, right? Can be used. Why can it be used? I mean, it's a simple operation, right? So, think of it this way. So, uh, you can think of it like this. So you had an A, okay? You what did you subtracted something from A? Uh, so you subtracted E from this thing. So this is the first graph. Then you did a division operation. So A minus E of A by some root variance of A. This is fine. Then what you did is you took this and then multiplied it with gamma, right? So there is a multiplication operation. So gamma times, so if it is a dash, so you did gamma times a dash. Then you did a addition operation. You did what? Gamma times a dash plus some beta, right? So I mean, this is a perfectly correct computation graph. So if any loss function comes, you can always in the reverse direction and back propagation is possible, right? So there is no issue with the back propagation also. So this is a correct statement, hence it's an incorrect option, right? So so this is the correct option. So I think only B will be the correct answer, right? So I think this was the ninth question. We are already 13 minutes above the time. Tenth question is very easy. Just plot the graph and you will see the all the options. It's not a difficult one. So I am leaving that as maybe you can do it as an exercise. Mm. So having said this, I think I have exceeded the time by a lot. So we will end it here. If you have any doubts or any questions, then you can ask. Then you can maybe ask it or otherwise we can end this meeting. Okay, so if you have any question, maybe you can ask, or otherwise we will end this. Okay, so okay, so thank you all. Thank you for attending this tutorial, and uh, uh, have a nice evening. Okay, I will end this meeting. Okay, all right.